Imagine a smooth, continuous wave of water flowing forward, only to suddenly crystallize and shatter into disconnected, rigid steps. In mathematical analysis, continuity is a local property. It describes how a function behaves as a spatial variable inches closer to a specific point. Convergence, however, measures what happens as an entire sequence of functions is pushed outward toward infinity. Calculus trains us to assume these operations are compatible, but the mathematical reality is that interchanging two different limit processes is highly unstable. They are not inherently commutative. You cannot assume that taking the limit of a sequence and then finding its spatial limit yields the exact same result as executing those operations in reverse. The mechanical flaw lies in pointwise convergence. This method evaluates a sequence strictly point by point, isolating every x value. Because it tests each point independently, the sequence possesses no global memory of the overall shape being constructed. Lacking that global structure, a sequence built entirely of perfectly continuous functions can snap under extreme limits, destroying continuity entirely. Walter Rudin lays out the mechanics of this failure in Principles of Mathematical Analysis. Looking at equation 3, Rudin explicitly states the main problem: whether important properties of functions are actually preserved under these limit operations. Pointwise convergence guarantees that the limits evaluate correctly at specific isolated values. But if you want to integrate or differentiate the resulting function, that isolated point checking is insufficient. To preserve continuity, we require a stronger condition: uniform convergence. This stricter rule forms the basis of modern approximation theory and functional analysis. It forces a sequence to converge uniformly across the entire domain at once, rather than point by point. To safely perform calculus on sequences of functions, the localized pointwise approach must be abandoned in favor of this strict global constraint. Theorem 7.11 proves exactly how this constraint operates by safely bounding the total error between a sequence of functions and a target limit point. Geometrically, this coordinate plane plots the distance we have to bridge. We need to find the total error between the limit function at a spatial variable t and a fixed target point a. To divide and conquer this total error, the proof relies on the triangle inequality, splitting the total distance into 3 measurable pieces. The first piece measures the vertical distance between the final limit function and an intermediate sequence function, bounded tightly by epsilon over 3. The second piece measures the spatial continuity of that sequence function itself. The third piece bounds the convergence of the limit points, utilizing the known properties of a Cauchy sequence. By adding these 3 independent bounds together, the mathematics dictate that the total distance is forced to be strictly less than epsilon. However, the triangle inequality only holds if the chosen index variable, capital N, remains valid everywhere. If n fluctuates depending on the spatial location along the x-axis, the entire proof collapses. Here is the structural deficit of the pointwise approach. It cannot guarantee a single static integer n that satisfies error bounds across the entire domain. This graph shows pointwise convergence in action. As you move along the curve, the required sequence index n skyrockets wildly just to keep the error bounded. Uniform convergence dictates the creation of a rigid global boundary, an epsilon tube running parallel to the limit function. This geometry locks n into place simultaneously for all points. This locked geometric boundary directly yields Theorem 7.12. By replacing the arbitrary target points from the previous proof with the functions themselves, the logic confirms that the limit function is strictly continuous. Uniform convergence acts as rigid scaffolding. By forcing the sequence to converge at the same rate everywhere, it prevents the structural tears that destroy limits. This establishes a rigorous rule, but it also creates a conceptual trap. If a sequence of continuous functions converges to a perfectly continuous limit, is that convergence automatically uniform? Walter Rudin introduces a specific counterexample to test this assumption. Look at this graph plotting the sequence on the open interval between 0 and 1. The sequence decreases monotonically, and as n approaches infinity, the limit function is exactly 0 everywhere. The sequence and the limit are continuous, yet the convergence is not uniform. As the function nears the 0 boundary, the curve sharply escapes any parallel epsilon band you draw around it, regardless of how large n becomes. This breakdown stems from the topology of the domain. Because the interval is open, it lacks the rigid boundary constraints required to trap the function's escape. Even if the starting sequence and the final limit are mathematically continuous, the transitional steps toward infinity will not be uniform unless the geometry of the space itself enforces it. Dini's theorem provides the exact conditions to correct this topological failure. By changing the domain from an open interval to a closed, compact set, point set topology forces a pointwise bounded monotonic sequence to upgrade automatically into uniform convergence. To process this, we have to change how we view these equations. We stop treating functions as curves drawn on a grid and start treating entire functions as single coordinate points located inside a massive abstract space. We map this new space using the supremum norm, a mathematical tool that measures the absolute maximum vertical distance between these function points. Theorem 7.15 states that applying this specific measurement turns bounded continuous functions into a complete metric space. Under this topological framework, uniform convergence is simply standard convergence, executing within the strict geometric rules of a complete space. Pointwise evaluation allows structures to warp and tear at their extremes. Uniform convergence bridges the local and the global, preserving continuity all the way to infinity. If you want to continue mapping the architecture of higher mathematics, subscribe below for more structural breakdowns of texts like Rudin.